if we want to get something more interesting from our solutions, we need to pick a different value for k, our constant that our x and t parts are equal to. So we'll pick k is equal to negative beta squared. We put the negative in there because we know what the solutions are going to look like at the end, and it's easier with a negative sign there. And we square it because we know it's going to end up getting taken the square root of later. So but for simplicity's sake, we'll just assume this form k equals negative beta squared. So if we write out our differential equations again, d squared dx squared for the x part, and we'll look at just the x part. The t part will look very similar. So we have that plus beta squared times x of x is equal to 0. And so this function of this form is a known solution to this differential equation is that x of x is equal to an exponential, e to the alpha x, some value alpha. We can test this and show that this is true instead of just taking it on faith that this is true. So we can just take the second derivative of e to the alpha x with respect to x. Okay, so that's going to be equal to, if we take one derivative, we'll get the derivative alpha e to the alpha x. So the derivative alpha e to the alpha x is alpha times e to the alpha x. And we take the second derivative and we'll get alpha squared e to the alpha x. And so we can show that then alpha squared e to the alpha x, this is our derivative up here, plus beta squared e to the alpha x, substituting what x of x is according to what we have here, is equal to 0. This is our equation up above, just with our x of x substituted here. And so we can factor this and say that alpha squared plus beta squared e to the alpha x is equal to 0. Now this part could be equal to 0, but that would be trivial again. So we don't want that. That's boring. And so we have to say that the constants, alpha and beta, when we add those together, alpha squared plus beta squared is equal to 0. Okay, and that gives us that alpha squared is equal to negative beta squared. So we want to solve for what these are, particularly alpha. Or we can say, or alpha is equal to the square root of negative beta squared, or alpha is equal to I times beta, plus or minus, right? Because it's the square root. So we end up with an imaginary number. This is why I went over complex numbers in the math chapter. So we can say that x of x is equal to, and we can have either plus or minus, alpha can be either plus or minus I times beta. So we have some combination, it can be possibly a combination of the two. So we could have part of it that is the positive, C1 e to the I beta x, and we could have C2 e to the negative I beta x. And with any values of C1 or C2, this will still satisfy the equation that we have. And so this concept of having function that's made up of two parts like this is what's known as a linear combination, and this will show up again later in our class. Okay, so we have found this formula. Now we have complex exponentials. That's not particularly nice to work with. Well, let's go ahead and switch this over to something that's a little bit easier. So we can use Euler's formula that we talked about in the math chapter, which again, as a reminder, is that e to the I, and we'll just use beta x here, either I x or I beta x is cosine beta x plus I sine beta x. So we can switch this from exponentials to trigonometric functions. And then if we have the negative, we'll get a negative sign in front of the I on the second part. So we can say x of x is equal to C1 times the sum of cosine and sine, cosine beta x plus I sine beta x, and C2 times cosine beta x minus I sine beta x. So we can combine terms here. We'll get C1 plus C2, just some constant times cosine beta x, plus I times C1 minus I times C2 times sine beta x. And so overall what we get is we get a solution that's a sum of a sine and some combination of a sine and a cosine. And so we can lump these constants together. We can give them a new name. We don't have to keep them as C1 and C2. And so we'll call this one A and this one B. And so overall our solution is A cosine beta x plus B sine beta x. And so our solution to the classical wave equation for the x part is that we have a combination of a sine and a cosine. And so in the next video, we'll look at how do we go from this to a final solution using the boundary conditions.